I'm Mani Kanuja, Principal Generative AI Specialist Solutions Architect at AWS, and author of 2 books on building these systems in production. Last time, the freeway showed you the shape of it, and peak flow arrives at a speed so slow that nobody would really choose it. So today, you draw yours. So stop thinking about your server as one number. Think of it as a curve, and by the end of this, you'll have drawn your own curve and picked your spot on that curve. So here are the axes with throughput up the side and along the bottom, the latency which your users actually feel. Only 2 axes, and what's a dot on there? One run of your server at one setting, and that's pretty much it. So why does one dot matter to you? Because the spot you pick on this curve will decide how many users you can serve on the hardware you have already paid for and how fast each one of them will feel your product. And most teams have never really picked that spot. You're sitting on one right now, and nobody chose it, it just happened. So, what does it really take to get those dots plotted, and what does it mean for you and your business? And how hard is this to run? 3 things you hold still, 1 thing you vary, 1 thing you plot. Hold the model still, hold the hardware still, and hold the shape of your traffic still. And this third one, the traffic, is what most people forget or skip. So, what do I mean by shape? It's how long your prompts are going in and how many tokens come back out. If you change those, then you're not drawing the same system's curve anymore, you're drawing a different system. And then you put the two side by side and reach the wrong conclusion. By holding these 3 things still, you are doing an apples to apples comparison. And that's what we want. So that's really the whole rule here. And it isn't special to inference. You are running a controlled experiment, so you only change the thing you are measuring and everything else stays frozen. So what does everything else include? Same model, same hardware, same server on the same version, and the same traffic shape on every single run. And next episode turns that into a checklist you can screenshot. Then you vary one thing, and that's concurrency, so how many requests you keep in flight at the same time. And you plot throughput against the latency one user feels, 1 dot per run. Do you have to loop a benchmark by hand for that? I used to, but you don't have to do it anymore. Because VLLM ships a sweep that does exactly this job. It sends your requests one at a time, first to get your lightest load, then all at once for your heaviest, then it fills in the middle evenly, and you can tell it how many points you want. One flag to change though, and it's on screen. It varies the request rate by default, but what you really want is varying concurrency instead, because VLLM's own docs say that's more reliable. Then it plots the trade-off for you. One honest thing though, does it pick your operating point for you? It does not, and it won't draw your target either. So that's the part which you have to decide. So before you draw your plot, let's first read a real one to understand how it works. These come from InferenceX, that's Semi-Analysis's open benchmark, and these are the version 2 results published in February, and I pulled them on the 6th of August 2026. The link's below, so go and read your own hardware off of it. One caveat before I say any of them. Where did they come from? It's a published chart, not a results table, so consider everyone as approximate. Focus on understanding the direction and concept instead of absolute numbers. So what does that look like on a real machine? Take a GB300 NVL72 rack. That's an NVIDIA server rack, and we're putting 8,000 tokens in and getting 1,000 back out. So that's a summarization workload, and I'm naming that shape out loud on purpose. That same rack, running that same model, can be operated at about 600 tokens per second per GPU, or at about 116 tokens per second per user. Same rack with same GPU. So that's 2 points on one curve. And one warning while the table's up. Each row runs that vendor's own best software stack. So this isn't the controlled experiment we just talked about. And don't read it as one chip beating another. And read the date off the corner there, because this suite keeps updating. Now 2 rows off that table, and I'd like you to answer before I do. Which of these 2 systems is faster? GB200, about 500 tokens per second per GPU, and about 130 tokens per second per user. GB300, about 600 per GPU, and about 116 per user. GB300 is the newer part, and it wins on throughput by roughly 20%, and it loses on the per user number by roughly 10. So which one is faster? Well, there isn't one answer, there are 2. and which one is yours will depend on where you live on that curve. So picture two products at one company, same model, same weights, and there's a chat product where somebody is sitting there reading along, so the only thing they will feel is how fast those tokens arrive. And on this data, you'd want the GB200 row. And there's an overnight summarization job. 10 million documents, nobody watching, finished by 6 in the morning. Nothing in that job will care how fast any one user gets served, so you want tokens per second per GPU there, because that's the bill you will pay, and that's your GB300 row. Same company, same model, and opposite hardware. And a spec sheet with one number on it will never tell you that. So why does the newer part lose on the per user number? I don't know for certain, and I'm not going to pretend that I know. Those two rows are quantized differently. So the numbers inside the model have been squeezed down to fewer bits, 4 on one row and 8 on the other. And we will do quantization properly in Module 7. Newer formats have newer kernels, and a setup tuned for the throughput end of a curve isn't tuned for the other end. So which one is it? Any of those, honestly. And it could also be noise in how I read the chart. But you still pick the right row anyway. So ask which one is faster at the point where you actually operate. So how do you pick your point? Take the target you set back in episode 5, draw it straight across your curve, and read off the most throughput sitting underneath that line. That intersection right there, that's your config. And one thing to add, because your SLO has two numbers in it, not one. A first token target and a per token target, so that's two lines, and you want the load where both still hold. So which one breaks first? Usually it will be the first token target as you pile concurrency on, because that's where your queue turns up. So work out which of the two is binding for you. Then stop right there. Right. Now the arithmetic, and this is where episode 5's SLO work finally pays you back. Remember MLPerf's interactive bar for Llama 270B? That was 40 milliseconds of TPOT, so flip it over. 40 milliseconds a token is 25 tokens a second to one user. And the human ceiling from that same episode was reading speed 2 to 300 words a minute. Call it 250, so roughly 4 words a second and around 5 or 6 tokens a second. And I do mean roughly, because words into tokens depends on your tokenizer and your language. Now back to that table. Those systems were doing 90 to 130 tokens per second per user. So what does that mean? Your hardware can generate tokens about 5 times faster than the bar a benchmark holds you to, and about 20 times faster than a person can read them. So if a person is reading your output, then most of that speed is wasted, and you will be paying for tokens nobody can perceive. Walk left along your curve instead, spend that headroom on throughput, and you can serve a lot more users on the same hardware, and every one of them will feel exactly the same thing. But is that always the right move? No, because episode 5 had a second branch, and here it will change what you do. If no human is reading it, if that output feeds another agent or the next step of a pipeline, then there's no reading speed left to beat, and that headroom isn't there after all. Something downstream is blocked on every token, so now you want the interactive end of that curve instead. And that's the same curve and the same hardware and the opposite decision, and all of it will depend on who is on the other end. So what won't your curve tell you? It'll show you that you slowed down. It won't tell you why. So which of the two walls did you run into? Compute or memory bandwidth? You will need the roofline for that, and we will cover it in Module 2. And today we walked the happy path on purpose, because the next episode will break it with a few specific ways a benchmark will lie to you, and most of them are one flag in your own command. So here's the one thing to go and do this week. Draw one curve for one model on your own hardware, then mark where you're operating right now, and mark where your target says you could be. For most people, those two marks will turn out to be in different places, and closing that gap is your next piece of work. See you next time.